Welcome to the lecture series on differential equations for undergraduate students. Today's lecture is on convergence and sum of the Fourier series. Till now in Fourier series we had learned that for a periodic function we can write a Fourier series for that function. We had also learned if the function is defined only on a finite interval on the real line, we can still extend this and write the either cosine series or the sine series, and we called it the half range expansions. In the plots of those Fourier series and the functions, we had seen that as with the partial sums we are including more and more terms, we are getting more closer to the function with the series. These things are how we are seeing is that is why they are matching and why they are not matching. Here is that now we are going to discuss this mathematical property of this Fourier series, which we are calling convergence and the sum of the Fourier series. For the convergence, as it is very easy to find out the Fourier series given any periodic function, we can find out the coefficients using the Euler's formula, or we can extend it to the even extension and or odd extension and get the sine and cosine series again using the Euler's formula. It was easy, but proving that the convergence or that why it is matching, that is a little bit more difficult and beyond the scope of this first level course. So, I will just quote here one result about this convergence of the series, which is due to Dirichlet. This result says, let f(x) be a 2 pi periodic function which is twice differentiable with f(x), f dash x and f double dash x are piecewise continuous on the interval minus pi to plus pi. Then for every x in the interval minus pi to the plus pi, the Fourier series a naught plus summation n is running from 1 to infinity, a n cos n x, b n sin n x, with coefficients a naught as 1 upon 2 pi minus pi to plus pi f x dx, a n as 1 upon pi minus pi to plus pi f x cos n x dx, and b n as 1 upon pi minus pi to plus pi f x sin n x dx for all n 1, 2, 3 and so on is convergent. Moreover, its sum is f x except at a point x naught at which f x is discontinuous, because we had assumed that f x is piecewise continuous, and the sum of the series is average of left hand and right hand limit of f x at x naught. That is, the series a naught plus summation n is running from 1 to infinity, a n cos n x plus b n sin n x is equal to would be same as f x when at all those points x where the function is continuous, and at x naught where it is discontinuous, at that point it would be equal to half of f x naught minus plus f x naught plus, that is the left hand limit at x naught and right hand limit at x naught. You take the average and it would be equal to that. Proof, of course, as I said, we will not be able to do here, but we can see this result from our examples which we have done for the Fourier series. So, let us verify these results with our examples. Now, let us see, we have done one example where our function was minus a in the interval minus pi to 0 and plus a in the interval 0 to pi, and the function was periodic with the period 2 pi, that is f x plus 2 pi is same as f x for all x. You to remember that in the last lectures we had find out the Fourier series of this as 4a upon pi sin x plus 1 by 3 sin 3x plus 1 by 5 sin 5x and so on. We had seen that at x is equal to 0, if I just see here in this particular example, the function is discontinuous at x is equal to 0. From the left hand, if I try to reach to the 0, I would get the value as minus a, while from the right hand side, if I try to reach to the point 0, I would get the value as plus a. which is not matching with the value of the, and the function is not defined at 0. So, this function is discontinuous at 0. Now, what is the average at this point? That is f0 minus plus f0 plus a plus minus a, that would be 0. Now, see the graph which we have drawn, that of the partial sums. This was the first partial sum, that is where we have taken only for a upon pi sin x. We see here that this is the function of in the minus pi to plus pi, minus pi to 0 it is negative of minus a, plus 0 to plus pi it is plus a. And the Fourier series, if you see, is that is, this is how we are going on. Now, at the point 0, let us see here, of course the same thing, because it is 2 pi periodic, so you will be getting is minus pi plus pi and all those things as such. See here at 0, average is 0. Now, this Fourier series we are saying is, that is at the point 0 we are getting it 0, while as at the points here we are saying is at some points we are matching. Now, you see this is my first partial sum, it is not the whole Fourier series. Let us move to the second partial sum. What we are saying is that as n is increasing, now if this is that n is equal to 1, we are having so much deviation from the actual values. Let us move to the second partial sum. Now, you see we have reached here. Now, the sum is okay, let us concentrate with minus pi to plus pi. We are here, we are seeing is that in between these points have been less from the previous one. You see in the previous slide we are having so many points in between. Now, we are having less points in between, and at 0 it is 0. The function is not anything over there, because here we are reaching to 0, that minus a. When we are reaching to from this side to 0, it is plus a. This one we are matching at certain more points over there. Now, if I go with the third partial sum, what will happen? This is your third partial sum. Now, we are at more points where we are making that we are equal to the function. At 0 we are all the time matching. Now, you see in the third partial sum, the points in between, all the points they have been disappeared, because the function is not anywhere in between this. At 0 we are not defining the function. Then if I move to the some 5 or 6 terms here I have taken, because I cannot draw it for a very large number of these things. Some 6 or 7 terms has been taken over here. Now, you see we are matching at many points. So, what we are saying is the function is continuous in the interval 0 to pi, the function is continuous in the interval minus pi to 0. The sum of the Fourier series, that is the partial sums which I am talking over here, they are matching with the points. At 0 where it is discontinuous, the value that the Fourier series we are having, this is the red points are telling us the point on the Fourier series, and this white are the function values. This is 0. So, we are saying is that as n is increasing, at the continuous points the sum of the Fourier series is equal to the here we could not say as actually equal to, but it is reaching towards the equal to the value of the function, while as when it is continuous it is coming at the average of these two limit points. Another example, you remember that we have done this example also, minus pi to plus pi, the function is x, again periodic with period 2 pi, f x plus 2 pi is equal to f 2 x. If you do remember, the Fourier series of this function was 2 times sin x minus sin 2 x by 2 plus sin 3 x by 3 and so on. Nth term is minus 1 to the power n plus 1 sin n x upon n and so on. Now, let us see its a partial sum and the graph of the function. So, first term 2 sin x, second term 2 sin x minus sin 2 x by 2 and so on. Now, with first partial sum, this is what is our function. From minus pi to plus pi, it is x. Then it is periodic. So, when we are reaching from minus pi to plus pi, this is the function. So, when I take it again this one, then it should start from here. This point which we are having is this line. This line I had purposefully put it so that you could see is that here is this function is not in between here. This is not the function value. There is no point on this line, you see. All the white points we are having over here. This just I am just trying to show you that is how you see now in the Fourier series this first partial sum. We are moving towards now at one point only, I think is we are matching with the function, and then we are not matching with the function, we are matching with the function at the 2 points here maximum, and at 0 the function is discontinuous at the limit points, that is at minus pi to plus pi. So, when this Fourier series is changing, you are finding it out from here to here. What is the average? Average is plus pi plus minus pi, that is 0. You say that is at this end points the value is 0. Now, here is one point, you are getting some points in between also. This is the Fourier series is not going to up to here, it is moving from here, because after that it is changing. So, because when we draw the graph, it would just take a curve like this one. This is first partial sum. Let us take the second partial sum, that is first two terms. Now, you see we have matched here more than those 2-3 points. In the first one we were matching only 1 point here, 1 point here, 1 point here. Now, you see we have matched a little bit more points over there. You see is that is more overlapping with the function. Again the points of discontinuity are this end points. So, here also now you see is that is at the last one we are having more points over here, now we are having less points over here, and similarly over here again, because when we are drawing this function, so it is curving out, so we are not again reaching towards this half one once. Now, come to the third partial sum. Now, you see we are matching little bit more, the function is overlapping quite nicely over here. The only thing is that is we are having is that you just come again discontinuity points, there the behavior is different. We are not still moving till the end because of this discontinuity, and at this point it is making this one, and because of that only, because we are just talking about first 3 terms only, so we are drifting from here itself. Now, let us move to the with some 8 or 9 terms. Again it is not more than 10, but still you can see how we are overlapping with the function, this white beads and red beads. You just see that is how at the points where the function is continuous, our Fourier series is matching with the sum of the Fourier series, that is the partial sum, that is because here it is not complete sum, it is partial sum. We are matching with this one. Now, you see we are reaching towards end points as well, and now in this between I do have only one point of the Fourier series which says it is average of the right hand limit and the left hand limit, and that point is 0. We are not having any other one. That is what we say is that is at the point of continuous, all those points the Fourier series sum would be equal to the value of the function, but at the point of discontinuity it would be equal to the average of the limit points. Let us see one more example, because those 2 examples were of the sine series. Now, here I do have this example 0 from minus 2 to 0 and x from 0 to 2. Now, you see this is not periodic with the 2 pi, this is periodic with minus L to plus L, and my L is here 2L is 4, periodic with fx plus 4 is equal to fx. This function, this examples also we have done in our last lectures, and we do know that from there we have drawn that the Fourier series is half plus summation n is running from 1 to infinity 2 by n minus 1 to the power n minus 1 upon n square pi cos n pi x by 2 plus minus 1 to the power n plus 1 sin n pi x by 2, or if I write it more elaborately, I would get half minus 2 upon pi whole square outside and cos pi x upon 2 square, cos 2 pi x over upon 4 square, so on, cos n pi x upon 2 n square, and then the sine terms 2 upon pi times sin pi x by 2 upon 1 minus sin pi x by 2 plus sin 3 pi x by 2 and so on. The nth term over in this Bn series would be minus 1 to the power n plus 1 sin nx pi by 2 over n. Now, here what will be the partial sum? When we were talking about only sine series or cosine series, we are taking only first term, second term and so on. Now, here when I would be defining the partial sum, I would be talking about the n is equal to 1. N is equal to 1 means is, that is, I would be taking both the terms, this cosine term as well as the sine term. So, my first partial sum would be half minus 2 upon pi whole square cos pi x upon 2 square plus 2 upon pi sin pi x by 2 upon 1, and the second partial sum taking up to this point and this point. It is not as we have to take first all these points and then go all these points, we are just moving with n. N means that is a n cos n pi x and b n sin pi n pi x by L. So, and this is a naught, so half this is there. Let us see the graph. So, the first partial sum. Now, the function is 0 from minus 2 to 0 and from 0 to 2 this is x. So, these white beads are showing you the function points at certain discrete points. This is the first partial sum. We do have that the function is continuous, but still it takes a step over here. We are, this is first partial sum, we are drifting away at certain points only over here we are matching on the downside, and then at certain points here we are matching. And because at end points, again at the limit points the function is discontinuous, so we are drifting away from there and we are not reaching towards the end of this one. Let us move to the second partial sum, a little bit more better presentation, but you see here we have drifted away and then we have drifted away over here also, and then we are matching towards these points. Now, you see here the points we are finding out that is continuous, all right, we are coming over here, while at here we are coming, this is the point of discontinuity. Now, you see many points in between, at the point of discontinuity it should have been, the point should have been somewhere in the between, that is from 2 to 0 I should have got somewhere at the 1, somewhere the point should have been, but this is only the second partial sum, we are drifting it one. Let us see some more third partial sum, we are again coming up, but because of you are finding it out, the function is, as we are having here is discontinuous at the end points and here in the between also, that is you are finding it out that it is 0 and from here it is actually looking as continuous, but at this end point it becomes discontinuous. You find it out that even when we were talking about only sine series, by the time of the third partial sum we were very near to the convergence, or we are able to come, that is my function is matching with the Fourier series, but here you are seeing is that is even at the third partial sum we are not having that nice kind of behavior of the Fourier series with respect to the function. Let us move to the fourth one. Again we are drifting this side also too much, as we are making is that here it is coming up very nicely, here it is coming close up, but we are drifting it away. What it is simply saying is that here with the smaller number of n's we will not be able to get that much nice behavior of the Fourier series with respect to the function, or here for showing that the Fourier series is matching we require more n, or this convergence requires a large number of n. I think is we do have here till fourth one only. So, you go till some 20 terms or something, only then you would be able to see this behavior, but theoretically it says is that for large n, as n approaches to infinity, you would get that the sum of the Fourier series at all continuous points would be equal to the function, and at the point of discontinuity it should be with the average of the two limit points. So, with certain simple functions we could see it very nicely, but here this example I have taken that you could see is not happening very early also, that is still fourth partial sum, we are not near to the our result. Now, one more terminology for this thing, that for the Fourier series of any periodic function f x, which we are writing as a naught summation n is running from 1 to infinity a n cos n pi x over L plus b n sin n pi x over L. This term capital A n, which is nothing but the square root of the sum of squares of the coefficients a n and b n. This is called the amplitude of the nth harmonic. That what it says is, in all those things what we have got is, that is the nth term means not a naught, nth term means is, that is if I take n is equal to 3, a3 cos 3 pi x by L plus b3 sin 3 pi by L x. This third term, this would be called third harmonic, because this is a periodic series. We do know that cosine function and sine function both are periodic. So, they would have some loop kind of things, and that is called the harmonic, and when this is called the amplitude of the harmonic. Now, let us see an application to the force oscillation. We have done such a Fourier series, that is where we are applying it in the differential equation. We have remembering, that is what we mean by the force oscillation. That means the differential equation is governing n y double dash plus c y dash plus k y is equal to r t, where n is the mass, c is the damping coefficient, k is the coefficient of the spring, and r t is that your input function. You remember that we have already solved this kind of equations, and there we have done this equation where this r t was of some special form. Let us just try one example which we have done, that spring mass system with governing force as y double dash plus 0.02 y dash plus 25 y r t, where your damping coefficient is 0.02, spring constant is 25, and the mass is 1 unit. This r t, if you do remember, we have now in this example, now my r t is, this input function is t plus pi by 2 in the interval minus pi to 0 and minus t plus pi by 2 in the interval 0 to pi. Moreover, this function is periodic, that is r t plus 2 pi is r t for all t. If you do remember, we have done that when r t is of the form that it is cos t or sin t, or it is some function e to the power t x kind of things. Now, how do we find out the solution of this equation? Let us just try. See what is my function r t. This is t plus minus pi by 2 plus t to this one. So, we are getting is at 0, we are getting is plus pi by 2. At minus pi by 2 we would be getting it as minus pi by 2, again at plus pi we would be getting as minus pi by 2. If you do remember, we have done one function t in the interval minus pi to 0 and minus t in the interval 0 to pi. and my RT is nothing but pi by 2 plus Ft. Now, you remember that we have done one result in the Fourier series which says is that if we do have the two functions, periodic functions for which the Fourier series can be written, then the Fourier series of the sum function is nothing but the sum of those Fourier series. So, now here we see this is a constant, this kind of examples we have done. So, we just want the Fourier series for this function Ft. Let us find it out. See this function Ft, we are getting is f of minus t would be same as minus of would be same as f of t. That says is that it is an even function. So, we would get only the cosine series. That means, all the coefficients Bn would be 0. What will be now a naught 1 upon 2 pi integral minus pi to plus pi fx dx. Fx here is, or this, if you replace this t by x, is x in the minus pi to 0 and minus x in 0 to pi. So, just break into the two parts, get this integral solved. Here it would be x square by 2 this integral, and you just put the values minus pi to 0 and 0 to pi, you get the answer as pi by 2. So, this is your a naught n 1 upon pi minus pi to plus pi fx cos nx dx. Fx again we are breaking into two parts, minus pi to 0 it is x and 0 to pi it is minus x. This is x cos nx. So, we will just go with this integration by parts. The first integral would be minus 2 upon pi, because the function is now x is odd and this cosine x is even. We are getting is that minus 2 upon pi 0 to pi x cos nx dx, which is minus 2 upon pi x by n, that is again integration by part, sin nx evaluated 0 to pi minus 1 upon n 0 to pi sin nx dx, which is minus 2 upon n square pi cos nx 0 to pi evaluation, and we get finally that minus 2 upon n square pi 1 plus minus 1 to the power n, which would be, that is for n 1, 3 and 5 it would be 4 upon n square pi, for n is equal to 2, 4, 6 it would be 0. That is what the Fourier series we have got. RT as 4 upon pi, summation n is running from 1 to infinity, 1 upon n square cos nt, which is 4 upon pi cos t plus 1 upon t square cos 3t and so on. Now, solving the differential equation, I will come to this, modify our differential equation. Y double dash plus 0.02 y dash plus 25 y is equal to 4 upon n square pi cos nt, that is nth term we have written from here. Our original differential equation was with RT. Rather than solving it with RT, now we are solving it with this nth term. That says is, since what we had got just now, that is from the convergence of the Fourier series, that the value at the value of the function at continuous points is same as the sum of the series. So, now we are using that idea. We are just solving at nth point, that is nth term. Now, if I solve it, now this is of a special form. We do know how to get the particular solution, or that, if you do remember, we have called it a steady state solution. The particular solution will be of the form a n cos nt plus b n sin nt. How to get these coefficients a n b n? We will just substitute y n dash y n double dash in this given equation and equate it to the right hand side and find it out. So, usual method, y n dash would be minus n times a n sin nt minus b n cos nt, and y n double dash would be minus n square a n cos nt plus b n sin nt. Substitute it in given differential equation, we would get minus n square a n cos nt plus b n sin nt minus 0.02 c times, that c is actually 0.02 a n sin nt minus b n cos nt plus 25 a n cos nt plus b n sin nt. This should be equal to 4 upon n square pi cos nt. Now, simplify the things. we do get 25 minus n square times a n plus 0.02 n b n cos n t plus 25 minus n square b n minus 0.02 n a n sin n t is same as, it should be equal to 4 upon n square pi cos n t. Now, equate the coefficients of cosine n t and sin n t on both the sides, we would get the two equations. One is 25 minus n square a n plus 0.02 n b n is equal to 4 upon n square pi. The coefficient of cosine n t have been equated. Second term is the coefficient of sin n t, 25 minus n square b n minus 0.02 n a n, right hand side it is 0. So, it should be 0. Now, these are two linear equations, solve them, we get the solution as a n as 4 upon n square pi, 25 minus n square upon 25 minus n square whole square plus 0.2 n whole square, and b n as 0.08 upon n pi into 25 minus n square whole square plus 0.02 n square. Now, we see the denominator in both the a n and b n is same. Let us substitute it as d. Then what we could write a n as 4 into 25 minus n square upon n square pi d and b n as 0.08 upon n pi d. So, we get the steady state solution for this modified differential equation as our actual equation, that is for this modified one we would get is that the yp is we are getting where this coefficient is a n and b n are being given by these values, and the solution would be a n cos n t and b n sin n t. Now, since we are talking about the linear equations, and the linear equations again we do know that the solution of linear equations, if there are two solutions for linear equation, then y1 plus y2 would also be a solution of the linear equation. Now, what we are having is that we said is that rather than that function f rt, we had substituted the nth term of the Fourier series, corresponding Fourier series into the term. So, what we are getting is that Fourier series we are getting the terms with 1, 3, 5 and so on, all the even terms were 0. So, now for our original differential equation, the particular solution or what is called the steady state solution, I could add up as y1 plus y3 plus y5 plus yn, where my yn is nothing but a n cos n t plus b n sin n t, with a n as this and b n as this. So, we will get the amplitude as for the yn, that is the solution for this modified differential equation, the yn is a n cos n t plus b n sin n t. Amplitude for this would be a n square plus b n square. If I do calculate, you have seen that is in the last one, that is a n was 4 upon n pi n square pi d, and then some terms 25 minus n square whole square and so on, and then I had added up the second b n square. What we do get, if you see this term, this is again your d. So, what we have got 4 square d upon n square pi square d square. That could be just simplified as 4 square upon n square pi square whole square d. So, what will be the amplitude? Square root of a n square plus b n square, that is c n. Now, we are calling this amplitude as c n for this nth differential equation you could call as a square root of a n square plus b n square, that would be 4 upon n square pi square root d. Now, put the values for different values of n, so that we could see that what would be the amplitude of the different solutions. A n is 4 into 25 minus n square upon n square pi d, b n is 0.08 upon n pi d, and c n we have got as 4 upon n square pi root d. Let us evaluate it for certain values of n. So, here I have done some calculations I am showing you here. You can do it this calculations by yourself as well. Let us see here. If n is 1, that is if I am having only the first term, then dn is this much, an is this much, bn is this much, and accordingly cn is this value. Just go on seeing this table. We are getting our dn, that is dn means is the d corresponding to this nth partial one, that is we are getting 576, 256, then 0.01, then again we are coming some large values, then again we are going to the large value. What we are finding it out at the n is equal to 5, this dn is very small, making it very small here because of this approximation. What I am getting is that an is approximated as 0, bn is some value. So, cn is contribution of the in the cn is only of bn, that you see is that cn is same as bn, but of course there would be little bit contribution, it depends upon that how much calculation you could do, but there is what the final calculations you can do. Now, what it says is that in the solution of the differential equation or the steady state solution, which we were having yps, y1 plus y2 plus y3 and so on, the term y5 that is ruling because of this one. Let us see that is what I am saying is and how it is working. Here is the function and y5. If you do remember, this was my function RT, and if I just make this graph y5, you are getting this graph. Now, let us come to this function and yt. Now, my yt is actually y1 plus y3 plus y5 plus y7, and I think is in the table I have taken till y11. So, here are also I think is the term till y11, I have added it up. Now, you see all other terms are not giving, or they are not dominating the nature of the solution as this y5 is dominating. You see, this is the term till 11th term I had seen, and you see here only y5, the 5th term, or we could say is y1, y3, so y5, so the 3rd term. You see is this, whatever is this nature oscillation which we are having here, that is dominated by this y5 rather than with any other one. So, this is very much dominating. This is what we are seeing is that amplitude is deciding that which one is much better approximation for that function. So, rather than using that solution of all those ones and solving it and then saying is, again you see here the convergence cannot be achieved in a small number of n's. For achieving the convergence you require a large one. So, this is your input function. This is actually this y is not actually the Fourier series for your RT. This is actually input RT and this is your output YT, but this output is dominated by one function only, that was y5. So, you see here we are having 3 1, I think is not very much missing. Now, you could see because you had seen this separately. Now, here I am superimposing all the 3. This is my input function, that is very clear. The output you are finding it out that both the lines are matching actually. The only point of the difference is here a little bit, which if you could see it out, that is your this pink color line is coming as your till here, and this another color, this one is it's more or less a white one, this is coming till here. So, you see is that y5 is actually dominating because of the amplitude only. Now, we have learned this Fourier series. It was very easy for any periodic function or even if it is non-periodic to get half range extensions, to get Fourier coefficients, approximate it as a Fourier series. Again we had learned that is with some partial sums or the Fourier series sum is being equal to the value of the function mathematically. Practically also we had seen that for certain functions very early with this third or fourth term only we are able to reach to the required place. For some other functions this takes little bit longer, that is in the value has to be some 20 or 25, but you do find it out that is we are reaching over that function. Then we had seen in solution in the first oscillation where we were able to solve only for functions which are of the form of cosine or sine kind of functions, but there we said as if input function is any periodic function rather than the sine or cosine, still we could give the output function and it is again oscillating. There we had also in our particular example we had seen that is what not necessary that whole all the terms of the Fourier series would be dominating, but only we would be getting is that is one or two terms depending upon that this harmonics and this amplitude we could find it out that which term is dominating, and only with that we can go ahead with the analysis. There is one more topic which I want to cover over here, that is called complex Fourier series. Is anything different over here? No. Complex Fourier series, when we are saying it simply I am using this as it simplifies our many calculations. So, you could say is that this complex Fourier series we are using many times where the calculations are much simplified than the real Fourier series, and you will find it out in further classes that this is how the things we are doing it, and when we want the real Fourier series we just go with the real components. The logic or the basis behind this is the complex exponential function. Do you remember it? Okay. It is, if you do remember or not, e to the power I n x. This is cos n x plus I sin n x. This is again also called as Euler's formula. And e to the power minus I n x as cos n x minus I sin n x. Now, from here what we could get, cos n x I can write as half of e to the power I n x plus e to the power minus I n x, and sin n x as 1 upon 2 I e to the power I n x minus e to the power minus I n x. What is this I? Remember that we are talking about the complex. So, this I is nothing but the square root of minus 1, that imaginary value. Now, let us see the Fourier series for any function we are writing as a naught plus summation n is running from 1 to infinity a n cos n x plus b n sin n x. Now, change this cos n x and b sin n x with these just now obtain the results in the terms of complex exponential functions. What I would get? The substitute it as a naught plus summation n is running from 1 to infinity a n cos n x I am substituting e to the power I n x plus e to the power minus I n x by 2, and with the b n again here by 2 is missing. So, it should be b n by 2 e to the power I n x minus e to the power minus I n x. So, we are getting this series. Now, this is the correct one. A naught summation n is running from 1 to infinity a n upon 2 e to the power I n x plus e to the power minus I n x plus b n upon 2 I e to the power I n x minus e to the power minus I n x. Do a little bit simplification. I can write it as 1 upon 2 a n minus I b n e to the power I n x plus half times a n plus I b n times e to the power minus I n x. That is, I have collected the coefficients of e to the power I n x and e to the power minus I n x. Rewrite it as C naught plus summation n is running from 1 to infinity C n e to the power I n x plus k n e to the power minus I n x. Obviously, C naught is nothing but A naught, C n is nothing but 1 by 2 a n minus I b n, and k n is nothing but 1 by 2 a n plus I b n. So, now we have got a new Fourier series, a new series where my terms are not cosine x and sin x, rather than I am having e to the power I n x and e to the power minus I n x. Now, the coefficients, this c n, k n and c naught, we have derived it from this original a n, b n and a naught. So, we can use the Euler's formula over here, that c naught is same as a naught. So, it is same as 1 upon 2 pi minus pi 2 plus pi f x dx. C n would be nothing but as is 1 upon 2 a n minus I b n. So, if I write the Euler's formula for a n and b n, I would get it as 1 upon 2 pi minus pi 2 plus pi f x cos n x, that is for a n, and f x sin n x, that is for b n. So, now here minus I b n. So, that is how we have got f x into cos n x minus I sin n x, a whole integral with minus pi 2 plus pi into 1 upon 2 pi. Similarly, we can now, if you remember, this is nothing but e to the power minus I n x. Then go for the k n, half a n plus I b n. Again using the same kind of formula, I would get it as 1 upon 2 pi minus pi 2 plus pi f x cos n x plus I sin n x dx. Now, I can write this as e to the power plus I n x. So, I am getting is 1 upon 2 pi minus pi 2 plus pi f x I n x dx. Now, you see c naught I am getting f x dx, c n I am getting f x e to the power minus I n x. This constant 1 upon 2 pi is same, the range of the integral is same, minus pi 2 plus pi, the difference is here. Then when I am coming at k n, I am getting the difference as e to the power I n x. Now, if I write k n as nothing but c of minus n, that is, if I replace here n with minus n, you will get that my k of n is nothing but c of minus n, and when I replace n is equal to 0, I would get it as 1, and that would be c naught. So, now you see what I have got. I have got the Fourier series minus infinity to plus infinity c n times e to the power I n x, because k n is nothing but c of minus n, c 0 is nothing but c n where n is replaced by 0. So, now you find it out that this is very compact form I can write, and that is what I said is it is easy in the calculation, where c n can be given as the formula 1 upon 2 pi minus pi 2 plus pi f x e to the power minus I n x dx for n 0 plus minus 1 plus minus 2 and so on, or you could write in another manner, that is minus 3 minus 2 and so on, 0 1 2 and so on. This is called the complex Fourier series for function of this is we have obtained for function of period 2 pi. Now, on the similar trend we can write for any function of the period of any 2l. What I have to change is, do you remember that is there it used to be cosine n pi by x by l and so kind of things. So, I would get it minus infinity to plus infinity c n I n pi x by l, where c n is nothing but 1 upon 2 l integral minus l to plus l f x e to the power minus I n x by l n pi x by l dx for n is taking value 0 plus minus 1 plus minus 2 and so on. So, this is now you see till now I was writing the Fourier series which is containing such a space, and then you have to write the 3 formulas, one for a naught, one for a n, another for b n. Now, we are writing only one formula, this is easy, and even the calculation is easy. You have to integrate only one integral and most probably 2. Let us see, that is with the help of an example. Find the complex Fourier series for f x is equal to x from minus pi to plus pi, and it is periodic with f x plus 2 pi is equal to f x. Remember, we have already find out the Fourier series for this function. Let us see how we are doing it in the complex one, and is it really making our calculations easy. So, let us see. we want a Fourier series of the form summation n is running from minus infinity to plus infinity Cn I n x, where Cn should be of the form 1 upon 2 pi minus infinity to plus infinity f x e to the power minus I n x dx. Now, calculate this one. If I do have here this n is equal to 0, I will not be having the function, and the function is x, and if I am having n not 0, then I would be having x times e to the power minus n x. We do know this exponential function that we can integrate and all those things, but if there is some multiple of the x, then we have to go with the partial one. So, we will break this into two parts. One is when n is 0, that is C naught, it would be 1 upon 2 pi minus pi to plus pi x dx, this is an odd function, it would be 0. Now, Cn for all n not 0, 1 upon 2 pi minus pi to plus pi x times e to the power minus I n x dx. Integrate by part, taking x as the first function, that is the differentiating function, and e to the power minus I n x as the integrating function. I will get 1 upon 2 pi x upon minus I n e to the power minus I n x evaluated from minus pi to plus pi plus 1 upon I n minus pi to plus pi integral e to the power minus I n x dx. The first evaluation, when we keep x is equal to pi and x is equal to minus pi, we would get it as 1 upon minus I is the I. So, I upon 2 n pi pi e to the power I n minus I n pi plus pi e to the power plus I n pi minus this integral 1 upon I square n square 2 pi e to the power minus I n x evaluated from minus pi to plus pi. Again evaluate it, we get it as I upon 2 n, this pi I am taking inside, e to the power I n x plus e to the power minus I n x plus 1 upon 2 n square pi, because 1 upon I square is minus 1, e to the power minus I n x minus e to the power minus I n x. Again simplify, we get I upon n cos n pi minus I upon pi n square sin n pi. What simplification we have done, that is cos I n pi plus e to the power I n pi x plus e to the power minus I n pi by 2, that is cos n pi. Similarly, here this divided by 2 I would be, if I am dividing it by 2 I, then I would have here minus I, it would be sin n x. So, now you see we have got a complex function or a complex series. Since it is cos n pi is minus 1 to the power n and sin n pi is 0 for all n, we are getting I upon n minus 1 to the power n, the coefficient C n for n not 0. So, let us see what is the complex Fourier series. Minus infinity to plus infinity I upon n minus 1 to the power n e to the power I n x, where n should not be or n should be not 0. So, if I expand it, it would be minus infinity to minus 1 I upon n minus 1 to the power n I cos n x minus sin n x and e to the power, and from summation n is running from 1 to infinity, because n is equal to 0 is 0, minus 1 to n power n upon n I cos n x minus sin n x. Finally, I would be getting it as n is running from 1 to infinity minus 1 upon 1 to the power n upon n minus cosine n x minus sin n x, which we could write like this one. Hence, finally, we would get summation n is running from 1 to infinity 2 times minus 1 to the power n plus 1 upon n sin n x. If you do remember that this was our real Fourier series which we had obtained in earlier example. So, here the thing is only that calculations, I do not have to go through that two kind of different integrals. Here this you could not have guessed that is a very simple one, because it was giving us only sine series, but if it is giving both sine and cosine terms, then the terms becomes real easy and the calculations are easy. That is why we are using this complex Fourier series, and from there we get what is the real Fourier series. That is all in this today's lecture about the Fourier series. So, we had learned the Fourier series, we had learned that is what is the convergence of the Fourier series in the terms that the sum of the Fourier series is equal to the value of the function at the point of continuity, and at the point of discontinuity the sum of the Fourier series is equal to the average of the limits, that is left limit and right limit. Then we had learned one more thing, the complex Fourier series. The complex Fourier series is not anything else, the only thing is that is using this complex Fourier series many times the formulation becomes easy, the calculations become easy and compact form, and from there we can come back to our real Fourier series. So, that is all in this Fourier series and today's lectures. Thank you.